Welcome to This Explainer, where we step into the exam newsroom to break down high-stakes Cambridge computer science questions and transform your answers from rough drafts into top-mark headlines. Now, I want you to imagine you're working under immense deadline pressure. You know the feeling, right? The clock is absolutely ticking down, the exam paper is sitting right there in front of you, and you have a massive task. You have to break down a complex story, which is the question, and deliver a precise, impactful headline, your final answer. Today, we are specifically focusing on syllabus code 0478. But listen, if you're taking 0417, 2210, or 9618, these exact same strategies are universally applicable, so stick around. We're going to be looking at two very distinct profiles of students today to figure out where things go wrong. First, we have Alex. Now, Alex absolutely loves the subject, but totally overloads their answers with raw computer science facts without offering any real analysis. It's just a data dump. Then we have Sam. Sam is really smart, but Sam constantly rushes. Because of that rushing, Sam completely misses the command word requirements. Throughout this entire masterclass, we're going to look at their flawed answers side by side with the examiner's actual red pen marks. We're going to dissect them, and I'll show you exactly how to transform those flawed responses into perfect top-tier scores.
Okay, let's take a quick look at the master blueprint for today. We're covering packet switching under pressure, decoding those tricky USB comparisons, catching transmission errors, cracking asymmetric encryption, and finishing up with the ultimate exam system.
Section 1. Packet switching under pressure. This is all about connecting the mechanics of the tech to the actual problem at hand. Right, before we tackle this massive question, let's take a step back and remember the underlying mechanics here. In data transmission, your data is broken up into these manageable little chunks called packets before it's transmitted across a network. Each packet has a header. That header contains the IP addresses, a sequence number, and then you have the payload, which is the actual data itself. But here's the thing. Understanding that theory just isn't enough. You have to know how to apply it when the exam throws a completely real-world scenario at you. So here is our first real Cambridge syllabus challenge. It's a heavy 6-mark question asking you to describe potential problems with live video conferencing. Now, you need to realize that 6 marks is often the difference between an entire grade boundary. The stakes are incredibly high here. The context provided is delegates in the USA and Mauritius, and the specific method being used is packet switching. Notice the command word here. It's describe. It does not say list, it doesn't say state, it wants you to describe. This is exactly where the story breaks, and you need to investigate the why and the how. Let's look at how our two students, Alex and Sam, handle this pressure. This right here brilliantly illustrates the difference between an average student who just lists raw facts about lag and a top-tier student who actively analyzes the underlying packet switching mechanics that are actually causing that lag. Look at item 1 on your screen. This is a classic Alex answer. Alex writes, sometimes you get echo or lag, lips don't match words, image freezes. Okay, sure, but Alex is just giving us symptoms. That's a rough draft, not a headline. Now look at item 2. This high-level student explains that video conferencing happens in real time, and the data is split into packets that physically take different routes through various routers across the internet. Because each route is totally independent, packets might arrive out of order, or they might even get lost along the way. The delay happens because the receiving station has to look at the sequence numbers in the packet headers and mathematically reassemble the data back into the right order. That exact reassembly time is what causes the video to freeze or the audio to drop out. You see the difference? One is just stating a symptom, the other is diagnosing the exact technological cause. Now, what's really fascinating about this slide is getting inside the examiner's mindset. They desperately want to see you actively connect the real-world scenario directly to the syllabus concept. The teacher's comments note that a high-level student doesn't just state that the internet is slow, that's way too vague. Instead, they identify that packet switching intrinsically isn't ideal for real-time streaming like a live video conference because of those variable route times. In fact, a truly top-level candidate might even go slightly beyond the immediate syllabus to suggest that a dedicated physical communication link like circuit switching would eliminate those timing issues entirely. That's how you show total mastery of the subject. So, the absolutely crucial point here is that a describe question demands all the main characteristics, effectively bridging the gap between isolated facts and analytical explanations. And this is exactly where we need to introduce the PEEL framework. If you don't know it, this is a massive secret weapon for Cambridge exams. PEEL stands for point, evidence, explanation, and link. Let's break it down for computer science. First, you make your point. Packet switching routes data independently. Then you provide the evidence. Packets take different amounts of time to reach the destination because they are taking different router hops. Then comes the explanation. Because of those different times, they arrive out of sequence and must be reordered using their sequence numbers. And finally, you bring it all home with the link. This reordering process is exactly what causes the freezing and lag in the video conference between the USA and Mauritius. Do you see how perfectly structured that is? If you apply the Peel framework to your descriptive answers, they transform from red marks to green check marks almost instantly. Before we continue with our strategy breakdown, listen up closely. Mastering frameworks like Peel requires consistent, guided practice. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Doing this ensures you're joining thousands of other students who are actively improving their grade boundaries every single week.
Moving right along, Section 2, Decoding USB Comparisons, or what I like to call the compare trap.
Okay, let's talk about USB, Universal Serial Bus. This is a form of serial data transmission where data is sent one bit at a time down a single wire. It is literally the global industry standard. But Cambridge examiners love to test if you actually know the specific technical differences between the older USB-A and the newer USB-C standards. In this scenario, you have a strict deadline to extract 4 distinct marks comparing USB-A to USB-C. This is the compare trap. When the command word is compare, you cannot, and I mean cannot, just list features of USB-C and completely ignore USB-A. You absolutely must provide a balanced analysis of both similarities and differences to get full credit. If you just talk about one, you cap your marks instantly. Let's see how our Rush student Sam handles this 4-mark challenge.
I want you to look incredibly closely at how the low-level answer loses marks by making vague statements without actually contrasting them, while the high-level answer pairs a similarity with a clear, direct difference. Sam's low-level answer says, "The cable works any way around since both ends are the same." Okay, actually, scratch that. This is factually incorrect on a hardware level. USB-C fits into a device any way around because the 24-pin connection inside the connector itself is totally symmetrical and non-oriented. It has absolutely nothing to do with both ends of the cable being identical. Furthermore, Sam writes, data access is much faster. You know what's going to happen? The examiner will immediately put a massive red line through data access. The correct syllabus term is data transfer. USB-C can transfer data at speeds up to 10 gigabits per second. Now, check out the high-level answer. It correctly identifies that both standards are backward compatible. Boom, that highlights a clear similarity. Then it contrasts the physical orientation, noting USB-A is one way while USB-C is non-oriented. Finally, it drops a highly specific fact. USB-C allows for 100-watt, 20-volt power connectivity, which lets it charge full-size devices like laptops, unlike USB-A. That is how you secure all 4 marks. This red pen breakdown from the examiner is absolutely vital to internalize. Inaccurate terminology like data access instead of data transfer will flat out cost you marks. As the teacher's comment clearly states, despite writing a full paragraph of text, Sam gained 0 marks, literally 0. This is the brutal reality of the exam newsroom deadline. If your terminology is sloppy, your headline gets rejected by the editor. You must force yourself to use precise syllabus-approved terms like backward compatible, non-oriented, and data transfer rate. Don't just make up phrases that sound kind of techy. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Precision in terminology is non-negotiable, and we're here to help you nail it every single time. Let's dive into Section 3, Catching Transmission Errors. Welcome to the Data Scan Workshop. Okay, so whenever data is transferred across any medium, there is always a huge risk of it being corrupted. We're talking about electrical interference, power spikes, or data skewing. To fight this, we use error detection. I'm going to put you on the clock. You have 60 seconds to visually scan this matrix. We are looking at a parity block using even parity. Now notice how intersecting row 8 and column 5 reveals the exact corrupted bit, breaking the even parity rule. Let's break this down together, step by step, because it's like a giant puzzle. A parity check adds a single parity bit to a string of binary data to ensure the total number of 1 bits is either an even number or an odd number. Since the slide says even parity, every row and column should have an even number of 1s. Look at byte 8 horizontally. Take a second to count the 1 bits across that row. 0, 0, 1, 1, 0, 1, 0. That adds up to exactly 3 1 bits. Well, 3 is an odd number. That instantly tells us row 8 has a parity error. But we aren't done. Now let's scan vertically down column 5. If we were to count all the 1 bits in that column from the full source data table, we'd find there are 5 1 bits. 5 is also an odd number. That indicates a transmission error in column 5. So where do row 8 and column 5 intersect? They cross exactly at the 1 bit in byte 8, bit 5. That 1 bit was corrupted during transmission. It should actually be a 0 bit. By using a two-dimensional parity block like this, we didn't just find out an error occurred, we successfully located the exact specific bit that flipped. Awesome, now let's move to our next error detection method, automatic repeat requests, or ARQ. We are doing a find the flaw challenge here. Our student Alex wrote the low-level ARQ answer at the top. Can you spot exactly why it loses marks? Alex mentions the words acknowledgement and timeout. Okay, that's good for maybe 2 marks. But it totally misses the trigger mechanism. How does the receiving device even know there's an error in the first place to ask for a resend? Now look at the high-level answer. This response meticulously explains the loop of cyclic redundancy checks, acknowledgements, and timeouts. It gives us the full Peel paragraph. It explains that the receiving device first receives an error detection code along with the data, typically a cyclic redundancy check, or CRC, which involves polynomial division of the data. If the CRC mathematical check detects an error, a negative acknowledgement is sent back to the sender. The sending device then waits a predetermined timeout period. If it gets a negative acknowledgement, or if it doesn't get a positive acknowledgement before the timeout ends, it automatically resends the data. That sequence, CRC, acknowledgement, timeout, automatic resend, is what guarantees top marks. Okay, let's dive into this specific teacher feedback, which highlights exactly why our third method, the echo check, is considered a highly unreliable error detection method in the Cambridge syllabus. You need to really understand the logic here. An echo check requires the data to be sent all the way to the receiver, and then the receiver sends an exact copy of that data all the way back to the sending computer to be compared. But think about the massive flaw in that logic. If the 2 sets of data are different, you have a massive blind spot. Did the electrical interference happen on the first journey to the receiver, or was the data perfectly fine and it got corrupted on the return journey during the echo? Because it's mathematically impossible to tell where the corruption occurred, examiners expect you to explicitly state this exact flaw when you are evaluating or comparing echo checks. Let's transition to section 4, cracking asymmetric encryption. And the subtitle says it all. We need to go way beyond saying just 2 keys. So whenever data is transmitted over public unsecured networks like the internet, we have to use encryption to alter the original plain text into unreadable ciphertext. Now, symmetric encryption uses a single identical 256-bit key to both encrypt and decrypt the data, which is fast, but sharing that single key over the internet to the person who needs to read your message is incredibly risky. It can be intercepted. That brings us to asymmetric encryption. Look at this question. This is a classic explain question, where you must provide evidence as to why the process works, not just what the process is. Again, decode the command word, explain. You have 4 marks on the line here. You cannot just define what asymmetric encryption is. You have to actively compare its safety mechanism against the inherent flaws of symmetric encryption. And this brilliantly illustrates the contrast between a basic pass and total mastery. Simply saying it uses 2 keys fails spectacularly, whereas defining the mathematically linked public and private matching pairs proves your expertise. Alex's low-level answer is a classic trap. Asymmetric uses 2 keys. The examiner reads that and thinks, so what? Why does that make it safer? The high-level answer dives straight into the mechanics. It explains that asymmetric encryption generates matching pairs, a public key and a private key, using a complex encryption algorithm. These keys are mathematically linked, but the crucial part is they cannot be derived from each other. So let's say Ollie wants to send Daniel a highly confidential document. Ollie takes Daniel's public key, which is completely public and known to everyone on the internet, and uses it to encrypt the plain text into ciphertext. Then he sends it. When Daniel receives it, he uses his tightly guarded, secret, private key to decrypt it. Because Daniel's private key never ever travels across the internet, the risk of interception during transmission is entirely neutralized. That is the why the examiner is looking for. So the crucial takeaway from the examiner's desk here is that without specifically detailing the independent roles of the public and private keys, your answer remains totally ungradable. The teacher is practically begging students to go deeper. You must explicitly mention the terms public key and private key, and you must clearly explain the one-way direction of the lock and key mechanism. Public encrypts, private decrypts. If you leave out those terms, you lose the marks. Simple as that. All right, we made it to Section 5, the final exam system. This is your ultimate blueprint for success.
I need you to memorize these 3 sequential steps right now. Rigorously decoding the command word, injecting precise syllabus terminology, and tying your facts directly back to the contextual scenario. First, always highlight or underline the command word the second you read the question. If it says describe, you use the Peel framework. If it says compare, you must balance similarities and differences. Second, apply a time management matrix. What I mean by that is ensure you are providing one targeted syllabus-specific fact for every single mark available. Don't write a massive 3-sentence paragraph for a simple 1-mark question, and definitely don't write one vague sentence for a 4-mark question. Use the exact vocabulary they want to see. Cyclic redundancy check, backward compatible, packet switching. Don't invent your own terms. Third, and this is where A-star students shine, always review your final answer against the real-world scenario provided. If the question is about a video conference freezing, your conclusion must explicitly state how packet reassembly delays cause that exact freezing. Tie it back to the story.
Listen, students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. You can't just watch this once and expect miracles. You have to train your brain to write this way. Here's your final reminder. Subscribe to our YouTube channel AC Exams at @ACExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @ACExams_IGCSE and click that bell. Don't let another exam pass you by without having this framework in your arsenal.
I want to hear from you. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the exams. Your Cambridge success starts here. Keep applying this blueprint, master your command words, and turn your exam pressure into perfect headlines. See you next time.